Today, we're diving into something pretty fascinating. We're looking at what happens when a totally new theory of gravity gets its very first stress test. And it's happening with brand new data from the Euclid Space Telescope. This is really science in action, watching an idea meet real-world observation for the very first time. Okay, so here's how we're going to break it all down. First, we'll talk about the galactic puzzle that got everyone thinking in the first place. Then, we'll introduce this new idea, dynamic vacuum field theory. After that, we'll see how it held up against Euclid's first data release, look at the, well, surprisingly strong results, and then we'll get to the big one, the decisive test that could really make or break this whole thing. All right, so right at the heart of modern astrophysics, there's this big puzzle. We see galaxies out there with wildly different amounts of stuff we can actually see. Stars, gas, what scientists call baryonic mass. But somehow, these very different galaxies can produce incredibly similar gravitational effects, like having the same rotation speeds. So the question is, how is that even possible? Well, the standard model, that's lambda CDM, it has an answer. It suggests every galaxy is sitting inside a big halo of dark matter, and you can basically just tune the size and density of that halo to make the math work out. But this newer idea, dynamic vacuum field theory, or DVFT, it comes at this from a completely different angle. It proposes that a galaxy's gravity isn't just about its mass, but about this coherent vacuum gradient state that it creates in the space all around it. And this is where things get really interesting. The very first public data from the Euclid telescope just dropped. We're talking about a massive new catalog of gravitationally lensed galaxies. This gives us this perfectly timed, incredibly powerful opportunity for a head-to-head quantitative test of these two competing ideas. So, how exactly does this new theory propose to solve the puzzle? To really get why it's so compelling, we need to dig into its core prediction. What is dynamic vacuum field theory actually saying? Okay, in a nutshell, DVFT says gravity is an emergent property. Think of the vacuum of space like a still pond. A galaxy, just by being there, creates these ripples and currents in the pond. This whole setup is what the theory calls a vacuum gradient state. And it's this organized, structured vacuum that actually dictates the galaxy's gravitational pull, not just the matter sitting inside it. Now, this leads to a really specific, totally testable prediction. The theory claims that the strength of gravitational lensing, which we measure with something called the Einstein radius, should be driven first and foremost by a galaxy's internal velocity, not its baryonic mass. This is the whole velocitous first hypothesis right here. So, you've got a clear prediction, you've got fresh off the press data, the stage is set for a confrontation. Here's exactly how this new hypothesis was put to its very first test, using that public Euclid data. The researchers basically compared two numbers. On one hand, they had a predicted Einstein radius. This value was calculated using the galaxy's stellar velocity dispersion, which is just a measure of its internal motion. And on the other hand, they had a modeled Einstein radius, which they got by directly analyzing those beautiful, warped images of the gravitational lenses themselves. The method was actually pretty straightforward. They grabbed a list of galaxies with high velocity dispersion from one Euclid paper. Then they cross-matched that list with detailed lensing models from a different public data release. And they found 9 top-tier grade A systems where they had both numbers available for a direct comparison. Okay, and this is a really crucial point. We need to be clear about what this test is and what it isn't. Because the prediction method itself is already based on a velocity formula, this first comparison is really more of a consistency check. It's asking, are these two different data pipelines from the Euclid team talking to each other correctly? It's a super important first step, but it's not the final decisive test. So with that important caveat in mind, let's actually look at what this initial pipeline consistency check found, because the results were, to put it mildly, pretty striking. And the result is what you're seeing right here. This plot is just fascinating. On the bottom axis, you have the predicted lensing strength, the one calculated from velocity, and on the vertical axis, you have the strength that was measured right from the telescope image. I mean, just look at how tightly those 9 data points are hugging that one-to-one line. It's an almost perfect match. And to put a number on just how tight that relationship is, the Pearson correlation coefficient, a scale where 1 is a perfect match, came out to 0.997. I mean, that's just an incredibly strong agreement. It's about as close to perfect as you can get with real data. And if we look at the error metrics, they tell the same story. The average offset between the prediction and the actual measurement was just negative 1.5%. And the other error metrics like mean absolute error and root mean squared error were also tiny. All of them were under 3%. And for anyone who really wants to get into the weeds, here's the raw data for all 9 systems. You can just look down that final column, the residual, which is the percent difference, and you can see it's tiny for every single galaxy. It just confirms this strong agreement across the entire sample. So that consistency check was a huge success. It validates the whole measurement chain and tells us that all the different parts of the Euclid data pipeline are working together beautifully. And this is great because it sets the stage for the real experiment, the decisive, falsifiable test that the theory actually proposes. This plot here gives us a little sneak peek. It shows the modeled Einstein radius against a proxy for the galaxy's flat rotation speed. And yeah, the relationship looks intriguing, but, and this is the key, to be a truly decisive test, a proxy isn't good enough. You need direct, completely independent measurements of that galaxy's velocity. And here's the game plan for that crucial experiment. Step 1. Find Euclid lenses that also have independent velocity measurements from things like radio telescopes or integral field units. Step 2. Correct the lensing strength for the specific geometry between us, the lens, and the background source. And then, step 3, the most important part. Look at what's left over. What do the errors, the residuals, correlate with? And it all boils down to this one huge question. After you've accounted for all the effects of velocity, do those leftover residuals track with the galaxy's mass? That's what the standard lambda CDM model would expect. Or do they track with the galaxy's shape and structure, its morphology? That's what dynamic vacuum field theory predicts. Answering that question, well, that's going to be a decisive step forward in figuring out the true nature of gravity on a galactic scale.